All right, let me mention one other detail about the definite integral before we talk about the u-Substitution integration technique. If f of x equals a rate of change of some sort, then your integral of that rate of change, a to b, f of x dx, if you think about what that would then provide you, if this is a rate of change, we do the integral, so that's like going, we're saying we've got rate of change like the velocity. The velocity is a rate of change. So if I do the integral of the velocity, won't that get me back to that position function or placement function? Like if we, because we're doing the antiderivative. Because if I have a position function, placement function, and do the derivative of it, that gives me velocity. So if I had the velocity and do the antiderivative of it, that gets me back to the position. Right. So anyway, having said all that, yeah, what this integral gives you is, which I guess we could say big F of b minus big F of a. If you do that computation, what that gives you is the net change from a to b. I guess we could say the net change of big F being antiderivative from a to b. Good example, like I said, is the velocity. Let's say if v is some velocity function. So if I integrate that from a to b, my velocity, let's say of t dt, well, let's just get specific about it. What that's going to give me is a position function. Sometimes we call it s, so we'll call it s here. And if we evaluate that from a to b, yeah, what that's going to give me, so s is the position function, or something for my object, whatever the velocity is of, and s, of course, is, or s prime is equal to v, s prime of t, equals v of t. Yeah, what that gives me, if this is a position, it gives me, the position at time b minus the position at time a. So if you subtract those two, that gives you the displacement, the net change in your position from a to b. So you're starting at, this says we're going to start at a, go to b. So if, we start here, and then it says I'm out here for b. The difference is what we're looking at, so it's the change between the positions. Now, that being said, we should say it's the net change. So this gives you the change in the position from a to b. Now, one other note here is, yeah, if we think about it in terms of how far the car, the object travels, does it actually tell me how far the car has traveled? Yes and no, because think about it. Couldn't this, let's say it's a car, velocity of a car. This is going to give me, from here to here, the change, from A to B. All right, well, what if the car has gone, it started at A and then it went to C out here and came back to B. You see what I'm saying? So it's not necessarily how far the car has traveled, it's how far net the car has traveled. So it's a net area. You know, we're talking, if you think about the area thing here, we're talking area under the curve, but as far as applying it here to the application, if you will, it's a net displacement is what we're talking about. The net change in position, I guess I should say. Displacement. Yeah, because it could have gone all over the place. So this is going to be the net change in that position. Because you'll have some positive, some negative, and you know the positives and the negatives. So anyway, just wanted to mention that. That's what, if you apply it to like to an application, like a rate of change, that's what you get. It's the net change. All right. So let me go ahead and go on to the u-Substitution. Like I was saying, the integrals, they can be sometimes difficult to find out. So I need to talk about different techniques of integration, which again, for our courses anyway, Calc 2 is a lot about that. But we're going to talk about the u-Substitution way of doing an integral. Let's start with a nice little example here. Yeah. Let's say I have the integral of 4x times x squared plus 5 to the 50th dx. Let's think about that for just a second. All right, here's the thing. Well, for one thing, you know, if we encountered, like if we had encountered this, not with the 50th power, with maybe a squared power, or maybe even a third power, one option would be, well, let's go ahead and square that out, multiply that out, and then distribute the 4x in, right? That's what we would have done in the previous section there. However, do we want to do that here? I don't think so, because this is the 50th power. And if we did x squared plus 5 to the 50th power, it'd take a while. So that's not really a viable option here. If there's something better, we want to look at it. And that's what we're talking about here. And that is going to be called u-Substitution. What I'm going to do is, kind of what's holding us back here is this. I mean, if it was just x to the 50th, I could, multiply those together. But it's because this inside part here is x squared plus 5. That's kind of the part that's holding us back. So what I'm going to do is label that in terms of a new variable, and that's going to be u. U is going to be equal to x squared plus 5. Okay? With me so far? Now, what I'm going to do, what the idea is, like I said, is to change from the x variable to the u variable. And then, I am trying to find the integral with respect to x, so change it over to u, and then when I get the integral of that, then I can come back to the x's. So it's kind of a roundabout way of calculating this integral. Now, here's the thing. To change from u to x's, I've got this in terms of u now, and I'll deal with the 4x in just a second. But so far, what I've done is I'm going to replace the x squared plus 5 with the u, right? But it's very important to change it over, because I want to do the integral now with respect to u, not x. So I've got to change this over from dx to du. Well, to do that, I can't just say it's du now instead of dx. I've got to make it valid here. And the way I do that is I use the differential stuff. Remember back when we said, when we were talking about differentials, y equals f of x. Well, when we were going through differentials, you remember what dy was equal to? dy was what? dy was equal to f prime of x times dx. Yes. We're going to go back to that right now. Because I don't have y equals, I've got u equals. U equals a function of x. So isn't u equal to this function derivative times dx? Or du, I'm sorry. Wouldn't du be equal to the derivative of this function times dx? That's just the same as we were doing with the y. But now we've got it in terms of u. That's just definition of the differential. In this case, it's the du instead of dy. Make sense? All right, so what does du wind up equaling? Well, like I said, the derivative of this is 2x. Just do the derivative of that times dx. And here's the way I like to handle it. What I'm replacing my dx. I need to replace it by something. So let's get this in terms of dx. Just solve for dx here. Divide by 2x. du over 2x is dx. And so that gives me just an outright replacement that I can make for dx. So now this goes in place of dx, so that's going to go right here. With me so far? Well, that just so happens to work very nicely because notice what happens with that denominator right there. Doesn't it cancel out nicely with the 4x in front? This x will cancel with this x, won't it? Because that's on top, that's on the bottom. And 4 cancels with the 2 and leaves me 2. So I've got 2. Here's all I have left. 2 u to the 50th du. This is nice. Because now I have, instead of x's, I'm doing u's. And I can do that antiderivative right there. That's a simple one, isn't it? What's the antiderivative here? Well, it'd be 2 times the antiderivative of u to the 50th is u to the 51. Of course, I have to put 1 over 51 in front of that, plus c. Or in other words, 2 over 51, u to the 51 plus c. However, we're not quite done because, again, we're doing this starting, we wanted the integral with respect to x. Well, we can get back to x here, can't we? Because we know what this is in terms of x. Just go back and resubstitute the x squared plus 5. 2 over 51 times x squared plus 5 to the 51 plus c. Okay? Questions or concern? Let's do another one. Okay? All right. See what we do on this. You know, some of them are pretty well straightforward. Others take, of course, a little more work. But it's the same in general thing every time when we're going to use this u-substitution. Again, the problem here is this inside part, right? If this was just the cube root of t, you know, I'd say that's t to the 1/3 power, antiderivative power rule it, I'm done. But it's not just the cube root of t, it's the cube root of 8t minus 3. So guess what I'm going to label u here? Well, u is going to be this inside part here, 8t minus 3. And then also, when you do that, you also need the du, which is just, du is just the derivative of this, which is nice. It's just 8 times dt. In this case, I'm doing t instead of x. And so divide that by 8, you got du over 8. That's going to be what dt needs to be replaced by. So now use these two things and make the substitution here. So what's that going to give me? It's going to give me the integral of, now it's just the cube root of u. That's what I'm going to replace the cube root of 8t minus 3 by. And then dt gets replaced by du over 8. Yeah, this is a nice, pretty nice little integral. Because now, in this case, this one's a little different because that 8 doesn't get canceled out, but that's okay because it's just a constant, right? You know, you can either think of it here, you can just say it's 1/8, and then of course I'm going to change the cube root of u to 1/3 power of u du. But yeah, du divided by 8, that just has a constant of 1/8 in it. This is just still just a nice little antiderivative, isn't it? Power rule. Do the antiderivative, so we have 1/8 times the antiderivative of this. Well, you add 1 to that, be 4/3, wouldn't it? So I'd multiply up front here by 3/4 reciprocal plus c. Do a little bit of simplifying here. That would be what? 3/32. Replace the u by what it was, 8t minus 3. We got it. 3/32, 8t minus 3 to the 4/3 plus c. All right? Okay. Here's another one. What about the integral cosine 5 theta d theta? Well, again, if I'd had just cosine of theta, no problem. Cosine 5 theta, a little bit of problem, not too bad. In this case, what do we assign u here to be? 5 theta. Yeah, u is just the 5 theta inside there. So du then, well, du would just be the derivative of this, which is 5, times d theta, which would mean du over 5 is going to equal d theta. Just divide both sides by 5. So if I make those replacements, u equals 5 theta, du over 5 is d theta, I have what? Cosine of u times d theta du over 5. Which is just like that one. The 5 doesn't cancel anywhere, so it's just the factor of 1/5 out front. Yeah, this is the integral of 1/5 cosine u du. That's just antiderivative cosine, isn't it? It's just sine plus c. Yeah, it's just 1/5 sine of u plus c, but the original integral was in terms of theta, so I need to go back to that, which just means replace the u back with the original substitution, 5 theta, 1/5 sine 5 theta. Plus c. Okay. Now, let's do this one real quick here. That's a fairly simple one with the trig function. What about this one? Think about this one. What if I have the integral of the cosine of x times sine cubed of x dx? Erase that. Go a little higher on the board there. All right. Well, maybe that one's not as obvious, u-substitution-wise, what we should do. Anybody want to hazard a guess? Well, let's rewrite this. Sometimes when we were doing the chain rule, we said let's write that in the alternate form here. That might help. If I rewrite this, sine cubed x means sine of x to the third power. Sine of x in parentheses to the third power. Rewriting it as such, yeah, this is a pretty complicated integral as far as the function there is concerned. And it's times, and as we know, just to reiterate, you can't do the power rule. There's not a product rule antiderivative. Yeah, you can't do the antiderivative of that. Well, even the antiderivative of that wouldn't be that easy anyway. But no, we have to look at some other options here. What if we were going to do a u-substitution? What would you want u to be? Sine of x, yeah. So yeah, I think writing it again in that alternate form helps you determine, yeah, u needs to be sine of x. Du then, well, du is the derivative of that, which is, what's the derivative of sine? Is it negative cosine? Now I'm talking derivative. Yeah, this again, we're doing both derivatives and antiderivatives in the same problem here, so be careful. Maybe I should have mentioned that earlier, but yeah, this is the derivative of sine. Derivative of sine is just cosine, isn't it? The antiderivative of sine is negative cosine, but the derivative of sine is just positive cosine. And then dx goes on the end of that. So du over cosine x is dx. All right, so what happens? Well, we make those substitutions. U is sine of x. Cosine of x, we'll deal with that in just a second. Matter of fact, right now. All right, so sine of x is u. So we've got u cubed in the middle there. Dx is du over cosine of x. What happens? Nicely, the cosine of x cancels. If it didn't, we'd still have a little bit of a problem, but because of that, yeah, we can do it this way. This just turns into the integral of u cubed du, which is a very easy antiderivative power. Now we are doing antiderivative here, so that's 1/4 u to the fourth plus c. Go back to what u is. U is sine of x, so it's 1/4 the sine of x to the fourth plus c, which can be alternately written as 1/4 sine to the fourth x. I don't care which one you use, but either one. Is it okay? All right. Funny you should ask that. Are we going to do any that don't cancel? That's what we need to do next.